Welcome, ladies and gentlemen, to the next episode of our calculus adventure. Today we will be doing some examples of our radius and interval of convergence from a Taylor or Maclaurin series. And so in this example here, I'm going to take a look at sine x centered at 0, so I will do a Maclaurin series on this one. And you can tackle this one in a couple of different ways. If you want to, you can go ahead and pause and take the 4 derivatives of sine just so you can get yourself into a good rhythm. Some of you, if you do this enough, you might actually start to remember the power series of sine, which is going to be p of x equaling x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial plus dot dot dot. Now, unless they specify how many terms they want me to go to, I usually go to about 5. That's just kind of my style, but I think the more important thing with this problem is getting yourself enough terms so that you can create a discernible pattern so that you can convergence test that summation. And so, if you're not sure how to get this, it's okay. We can do this the long way. It's not a big deal. Remember, a Maclaurin or even a Taylor series is modeled from this. You get p of x equaling f of 0, and if you want, you can fast forward through this part. If you remember the power series, you can go ahead and skip to the next part of this, to the convergence section of this. F double prime of 0, x squared over 2 factorial plus f triple prime of 0, x cubed over 3 factorial plus so on and so forth. All of the ones that have sine, because we're taking this at 0, all the ones that have sine are going to go away, so I don't really even need to worry too much about this guy or even the fourth one. It's the ones with cosine that are going to matter. So I get p of x equaling f prime of 0, which is cos. 1 times x is x, and then it's going to be negative cos, so it'll become negative 1 x cubed over 3 factorial, and the pattern will emerge from there, just like we see in our power series. And again, it doesn't really matter what we're going to be doing with here in terms of how many terms. I really just want to get enough terms so that we can be able to establish a pattern. Now, I am going to tell you what a very terrible mistake would be. Here, I'm going to write my general term here for this pattern here. The general term, since we're alternating, is going to be negative 1 to the k plus 1. And each term has an x attached to it, so I'm going to call him x. And then the slope of each exponent, so if I call him 1 here, x to the first, the slope is going up by 2 each time, so I know it's going to be 2k, and how I get to the 1 and the 3 is going to be minus 1. And it seems like the bottom is doing the exact same thing, so 2k minus 1 factorial. Now let me tell you the mistake you are going to make. This would be terrible. If you did this, this is actually wrong. You don't do that. Because what this is saying is it's saying that your p of x is going to be all of these terms plus this summation that begins at 1 again. So, given the fact that the AP exam has FRQs in it, in fact, this year is pretty special. It's all FRQs. If you write this down, you're blasted, right? They will take off points very, very freely. So we are not going to put the sigma right there. If you want to write a sigma notation, then what you do is you create another line down, and then you say, okay, cool. So all of this culminates into this expression right here. So again, please don't put the sigma in the wrong place, because if you do, you will be having points put into minus world for you. So don't do that. Do not. Okay, so let's go and find the radius and the interval of convergence here. Now, actually, in class, someone had asked, so what is the radius and interval convergence of sine? It seems like the more terms we add, the more accurate we're getting. And so, in fact, let me show you that. So no surprises here. We've seen this graphic before. I have my sine curve. I have my summation right here. And so since I'm only going from 1 to 2, we're not totally accurate. But if I make him suddenly, if I make him suddenly 10, we're looking really, really accurate. And in fact, I don't know what this point is doing here. I'm going to go ahead and delete him. I don't like him. Can I get rid of him? I did. Good job. Thank you. So from here, I will now, as we saw when we were learning this, the more terms I add, the more accurate it gets. And I really like when you start putting lots of numbers in there, because then it slows the calculator down so you can actually see it physically being drawn. And so the reason why I brought that up is because someone had asked, so what's the interval of convergence on this thing? It seems like the more terms we add, the more accurate it gets. And I had mentioned that the interval of convergence for the sine power series is actually negative infinity to infinity. Well, let's see why that is. I'm going to go and take the limit as k goes to infinity. I'm going to employ the ratio test for absolute convergence, and that's because we have these factorials happening, and we have these k's and the exponents. The ratio test for absolute convergence is definitely going to become a thing. So let's get rid of this alternator by saying x to the 2k plus 1 minus 1 over 2k plus 1 minus 1 factorial times 2k minus 1 factorial over x to the 2k minus 1. A lot of algebraic mumbo-jumbo happening here, but we can handle it. It's not totally bad. So this will simplify into x to the 2k plus 1 over, this is going to become 2k plus 1 factorial times 2k minus 1 factorial over x to the 2k minus 1. Oops, not minus 1 down there, but minus 1 up here. Again, a lot of algebraic manipulation. Just stay with me if you can. If you don't want to, just go and fast forward. I understand the limit as k goes to infinity of the absolute value of x to the 2k times x over this 2k plus 1 factorial is really going to be 2k plus 1 times 2k times 2k minus 1 factorial, and then this 2k minus 1 factorial here is going to then eventually cancel itself out. So we will see that happen. Times 2 to the negative 1 here. So what's going to get out of here? Let me switch to catch up here. Let's see. Goodbye to the 2k minus 1 factorials. Goodbye to the, I don't know why I put a 2 right there. That's supposed to be an x, but it doesn't matter because he's gone anyway. And what I end up with is after all that mumbo-jumbo is canceled out, I end up with the limit as k goes to infinity of x, and I don't know what this is doing here. That's not, I don't know why I kept putting a 2 there. That's an x to the negative 1. So that bounces up and becomes x squared over 2k times 2k plus 1. Now, when it comes to radius and interval of convergence, if you were a lazy calc student, this is a very great scenario, because as k goes to infinity, it doesn't matter what x is. K is the thing that we're taking the limit of. This guy ultimately just goes to 0. And no matter how you cut it, 0 is less than 1 for every single number imaginable. So, unlike the example in the last video where we had to test endpoints, because this one didn't give me an x as a remaining anything, we can conclude then that this polynomial will then converge on negative infinity to infinity. That is its interval of convergence. And we saw that happen in the TI Inspire. The more terms we added, the more the red converged on top of the blue. More. So I hope that makes sense to you. And yeah, we will then move on to the next example. Give me a second. Alright, so in this example here, we're actually not given a polynomial function that we're going to have to construct. They actually give it to us in summation notation already, and you'll see that in the homework. And so it's important to note that this is not centered at 0, so this is a Taylor series, and this was your dead giveaway right here, this x minus 4. And so with this in mind, let's go ahead and just jump straight forward. We're going to find the radius and the interval of convergence of this thing. And so again, I'm going to start off with my ratio test for absolute convergence. So it'll be the limit as k goes to infinity. The absolute value removes the alternator, so I'm going to get x minus 4 to the k plus 1 over k plus 1 squared times k plus 1 squared over x minus 4 to the k. Okay, so now from here, what we're going to do is we're going to just cancel some stuff out. So that guy's going to go with that guy, and I think that's all we've got. So I'm going to say the limit as k goes to infinity of, looks like, x minus 4 times k plus 1 squared over k plus 2 squared. Now, unlike the last example, this time, as k goes to infinity, well, these guys are of the same ilk. They're of the same power, which means this guy is going to go to 1, which is going to leave me with the absolute value of x minus 4. Now, unlike the last one, the absolute value of x minus 4 is not always less than 1. So I'm going to have to go ahead and set him to be less than 1 so that I can solve for my x domain, or my interval of convergence. Once you get this far here, your radius of convergence is going to be 1. And that's because of this guy. Now, if you're wondering, well, isn't it always 1 then, because you always set it less than 1? That's not true. And we will see an example of when that actually doesn't happen. So from here, you can solve this using some integrated 1 skills, or if you know that this guy's centered at 4, you can go ahead and just draw a number line, center him at 4, and you know that absolute value is a distance, and this distance is going to be 1 away from that 4, so which means 5 is your max, 3 is your min. So your interval of convergence is going to be between 3 and 5. The last thing we have to figure out is what types of brackets we're going to have around the 3 and the 5. Are we actually converging on 3? Are we actually converging on 5? Or are we just converging super close to 5, but not actually there? Well, how do we do that? We use our summation, and we plug in the 3 and the 5 in for x. Not for k, for x. So, at x equals 3, well, what's that going to look like? That's going to be the summation from k equals 1 to infinity of negative 1 to the k because of our alternator. Now, 3 minus 4 is going to be negative 1, so that's going to be negative 1 to the k also, over k plus 1 squared. Well, what's that going to give me? Well, that's going to give me from k equals 1 to infinity of negative 1 to the 2k over k plus 1 squared. And it seems like since this is 2k, if I plug in a 1, I get a 2. If I plug in a 2, I get a 4. If I plug in a 3, I get a 6. There's no escaping it. This 2k will turn this negative 1 into an always positive situation. So I'll go ahead and do that. Now, before you get all bent out of shape about this here and start wondering, well, how can I prove this thing converges? Well, it's actually not that bad. It's a pretty familiar looking scenario. One might say this sequence right here reminds me of something easy. And if it reminds me of something, I can bust out my good old buddy, the comparison test. I'll compare him to, if I actually FOILed him out, I would get k squared plus 2k plus 1, which is going to be a p series with p being greater than 1, so I know this is going to converge. So what I'll do is I'll go ahead and compare him to 1 over k squared. Now this one here, if you're not comfortable doing a direct comparison, limit comparison will get you the same thing. We'll compare them to 1 over k squared, and what I'm going to do is I'm going to say, okay, 1 over k squared versus 1 over k plus 1 squared. Well, remember, when it comes to direct comparison, it's always best done when the functions are easy to actually compare in your head. From here, And if we're doing a direct comparison test, I know that my 1 over k squared is converging, so this 1 over k squared needs to flatten out this 1 over k plus 1 squared, which means it needs to come in from above. Well, luckily, it does. How do I know that? It's because when you have when you have a larger denominator, it means you have a smaller overall number, especially because the numerators are exactly the same. So this is true for all k greater than or equal to 1. So understandably, it's been a long time since we've done direct comparison. So what are the rest of the qualifications that I need? Well, I know this is going to be true, and I can say that 1 over k squared is a p series with p being greater than 1 and therefore converges. And then I can go and type out the rest. I can say then, therefore, by direct comparison, the series must also converge. And I'm going to leave myself a little bit more space there so I can actually draw in the summation. From k equals 1 to infinity of 1 over k plus 1 squared. Now again, you could have done limit comparison. It would have been totally cool. You would have gotten 1, which is finite and positive. It's up to you. And I'm running out of space here. So let me see if I can fudge this in. Okay, so that is what's happening at x equals 3. So actually, before I even move on to the next part of the problem, I will go ahead and just throw down a hard bracket right there, because I know I'm converging actually at 3, because I converged at that number. Well, let's take a look at what happens at x equals 5. So it's going to be the summation from k equals 1 to infinity of negative 1 to the k. That's my alternator. If you look back at the original series, it'll end up becoming 5 minus 4 to the k, so that's going to be 1 to the k over k plus 1 squared. And 1 to the k, well, he's easy. He's just 1, so we don't care about him. So the summation will start from k equals 1 to infinity, negative 1 to the k over k plus 1 squared. Well, this is a really good position to be in. This is an alternating series right here. So we can then say that a sub k is alternating, a sub k is decreasing in absolute value, and the limit as k goes to infinity of a sub k equals 0. So we can say, therefore, the summation of negative 1 to the k over k plus 1 squared converges by alternating series. So, because we are converging actually at 5, we are hard bracketed in. From 3 to 5, we are converging, and our radius of convergence is 1. Okay, let's see if I can't squeeze in one more example. Alright, let's take a look at this Taylor series here, centered at 3. And we're going to find the radius and the interval of convergence of this guy. So from here, the limit as k goes to infinity. Again, I'm just employing the ratio test for absolute convergence here. This is going to be x minus 3 to the k plus 1 over 2 to the k plus 1 times 2 to the k over x minus 3 to the k. And so after all the algebraic manipulation is done, I'll probably speed this one up just a little bit here. I end up getting those guys to cancel each other out, those guys to cancel each other out. I end up with simply an x minus 3 over 2. Now, if I take the limit as k goes to infinity of this expression, well, there's no k in sight. So actually, it's almost like taking the limit of a constant. So that's what it results into. If I take the limit of a constant, I get a constant. And then I'll go and compare him to 1. So in the last example, I know what you were thinking. You were thinking, wait, the radius of convergence is always 1 because we always compare this guy to 1. In this case, the radius of convergence is not going to be 1. And that's because this expression here is really the absolute value of x minus 3 over the absolute value of 2, which is really 2, setting him less than 1. Which means that my x minus 3 in absolute value will be less than 2. And that means right now that the radius of convergence is 2. And if I draw a number line here, 3 is my center, 5 and 1 are going to be my endpoints. So I know that my interval is going to be from 1 to 5. Now again, I don't know if I'm actually converging there. I do have a reasonable suspicion, but that's because I've done this problem a couple times already. But yeah, let's go and just test it out and see what happens. At x equals 1. And if you want to, you can go and pause and see if you can get this before I do, and then that way you can compare answers with me. Looks like I'm going to get negative 1 to the k for the alternator. And if I plug in a 1 into the x minus 3, I'll get negative 2 to the k over 2 to the k. Whoops, too large. 2 to the k. Okay, well, check it out. Because these are both being raised to the same exponent, I can actually multiply those bases together. And so what's going to happen is I'm going to get 2 to the k over 2 to the k. And that's a summation right there. Which means I'm just taking the limit of 1. So the limit as k goes to infinity of 1 is going to be 1. Which in this case, it's hard to tell which test we actually used right now, except we know which test we used. We're going to compare them to 0. And because 1 does not equal 0, we can say this guy diverges by what they call the Divergence Test. So at the end of the day, this guy, he'll be adding 1, and then 1, and then 1, and then 1. He's just going to diverge out into space. So before I move forward, my 1 is going to get a soft bracket. And then I'll go and just do my x equals 5. That's going to be the sum from k equals 1 to infinity of negative 1 to the k for my alternator. And that's going to be, looks like 2 to the k if I do 5 minus 3 over 2 to the k. Oh, that's awesome. These guys are gone. So what I get is the sum from k equals 1 to infinity of negative 1 to the k. I can then say that the limit as k goes to infinity of negative 1 to the k, there is no limit due to oscillation. So therefore diverges, again, by the divergence test. But sometimes I just want to give you guys a heads up on this. Sometimes they call this the nth term test. They're the same thing. And so just to let you guys know, they are interchangeable. You know, you say tomato, I say divergence test. So just make sure you guys are keeping that in mind, because the AP exam likes to vary up the vocabulary and the terminology on you. So this is going to be soft bracket 5. Now, you might have been able to tell that this was going to end up geometric, and why these guys weren't going to work, because the alternator, the alternator and everything shares the same exponent. And so, and we've seen this before, where we see an alternating geometric series that converges. And remember, in a geometric series, as long as the r value, which is this guy, is less than 1, we would converge. But in this case, because this is geometric in nature, it has to be less than and not less than or equal to, unlike some of the examples we saw before, where you actually were converging at the point in question. So just stuff to think about for you guys. I think that will wrap it up for these 3 examples. As always, please leave comments or questions in the comment section, or just write them down and we can ask them during class. You know I enjoy hearing your feedback. And that will be it for this one. So thank you for watching, and I will see you in the next episode.